Greetings, and thank you for joining me for our Gene Therapy 2.0 technical seminar. My name is Mike Bransby, and I'm the R&D Director for Filtration, working primarily out of Repligen's Southern California office in Los Angeles. Our topic today is centered around increasing bioreactor productivity of lentiviral vectors for gene therapy applications, which was done in partnership with Oxford Biomedica, using a very new filtration technology called TFDF. This is just one application of this technology, and we don't have a lot of time together today, so I'm going to focus on the yield benefit and then describe in general terms that the technology is fast, requires a very small footprint, and is operational simple even at larger scales. If you'd like to learn more about how the technology works or other applications, I encourage you to contact your local Repligen sales representative or visit repligen.com. The title of the webinar is Increasing Lentiviral Vector Bioreactor Yield with Simplified Execution Using Tangential Flow Depth Filtration. As we survey the viral vector workflow, Repligen has developed and launched many solutions to help with different pain points. If you're looking for a faster or better way to complete your unit operation or analytics, give us a call. Today, we are focused on viral vector production and specifically the clarification steps, where there are some clear needs in the industry. I've been in the gene therapy area for over 15 years, and the harvest step has always been a great challenge. Can we get increased viral vector yield with gentle methods that are lentivirus compatible in a closed aseptic format? Hopefully, you'll see that we're addressing several of these needs with the new TFDF technology. Okay, the case for an increase in viral vector yield is supported by a model built and published by Renninger and others in December of last year. Their model incorporates the number of active clinical trials, average yields, and requirements per indication to create a plot of the number of batches required per year. The projected demand for viral vector is plotted in orange, while the supply, how much can be produced worldwide, is in blue. Two different models were created with different rates of capacity growth. But both models, however, conclude that total demand will exceed total capacity even this year. So if you look, the curve in the orange is going up almost exponentially. That is, the demand is great, but the capacity is flattening off. And so there's this big disparity. So you've heard about flattening the curve for COVID, which we all want to do, and it keeps going up and down. We want to keep the COVID curve flat, but we don't want to keep this curve flat. We want to get capacity supply to meet demand. We believe TFDF is a potential way to do that for your processing. Oxford Biomedica was the first to develop a commercial lentiviral-based gene therapy delivery system, and they have transitioned their adherent HEK293 cells to suspension bioreactor in order to increase yield. Repligen is a leader in high-impact bioprocessing technologies, the latest of which is TFDF, or Tangential Flow Depth Filtration. TFDF is the first depth filter that runs in tangential mode. In order to accomplish this, the filter is tube-shaped and is not a dead-end filter. In this picture, we have a bioreactor that contains blue HEK293 cells and orange lentivirus particles. The bioreactor feed is connected to the bottom of the tubular TFDF filter, Permeate, shown here in orange, travels through the wall of the tube, while retentate continues through the lumen and the end of the tube, and then is directed back to the bioreactor, not shown here. So you have the blue cells recirculating back into the reactor and the orange lentivirus particles coming out. An integrated system with pumps and software runs this automated process. This brings us to the two key questions raised when Repligen's TFDF technology met Oxford Biomedica's suspension culture. First, can TFDF improve the harvest unit operation over classic depth filtration? And second, because the cells are preserved, that is, they're continuing in the reactor, they're not getting stuck in the filter, can they be used to create more virus in a high productivity mode, which is also frequently referred to as batch perfusion? You can read about the detail of the work in the Cell and Gene Therapy Insight article published this year. The first experiment is a straightforward comparison of TFDF and depth filtration at the 5-liter scale using a therapeutic lentivirus. When normalized against bioreactor titer, depth filtration delivered a yield of approximately 70%. They're in the salmon color. TFDF in comparison delivered a yield greater than 90%. Clearly, the TFDF transmits the virus. But why the increase in the yield? Well, there are several reasons. The first is that the nominal pore size of the TFDF filter is 2 to 5 micron, meaning that while holding back the cells, the 100 or 120 nanometer size lentivirus particle has plenty of room to navigate the channel. Second, that the filter material, which is completely synthetic, primarily built of polypropylene, does not bind the product. Thirdly, because of its high capacity, a TFDF filter is more than 10 times smaller than a depth filter, and therefore it has very low holdup volume. Together, they more effectively separate the cells away from the product. So I want to show you a graph that brings out the advantages of TFDF filtration in a bit more detail. The x-axis of the plot is time, and then we have two different y-axes. The first is the pressure, and the second is the flux. TFDF typically delivers flux rates up to 10 times greater than depth filtration. In this example, flux starts at 750 LMH and remains stable at that value over the course of the entire run. On the left axis, let's look at TMP. In contrast to a dead-end depth filter, TFDF directs the great majority of the cells away from the filter rather than into the filter. The product and cells, therefore, do not compete for access to the same channels, and the system becomes very robust to fouling. TMP for the run starts at a very low value of 0.5 psi and increases 0.25 psi at the end. So it's really low. This is essentially no fouling of the filter. The last point here is time. With a flux of 750 LMH, the operation can be completed very quickly. In this example, 5 liters was clarified using a 50 square centimeter filter in less than 1 hour. To put that in perspective, the filter for 5 liters is about the area of the palm of your hand. The combined depth filter with tangential flow, the cells going back to reactor, not getting stuck, enables it to process very quickly and be that compact. Let's take it one step further. TFDF returns the cells to the bioreactor and does not foul, which begs the question, is this process gentle enough to reuse the cells? We're all in quarantine, well, still are, after 9 months, and lots of people are making sourdough bread. My wife is also on the bandwagon, and she keeps the starter in the fridge and feeds it every once in a while so she can do multiple batches of sourdough bread. So can lentivirus production be run in this high productivity kind of mode where you can get multiple batches out of the same cells? It's also referred to as batch perfusion to some. Well, the answer is yes. Using a 5-liter sub single-use bioreactor and an HIV GFP virus, a first harvest was executed at 750 LMH, delivering a yield greater than 90%. The fresh media was added to the bioreactor, cultivation was continued, and then a second harvest was executed once again at 750 LMH. Without optimization, the yield for the second harvest was 85%. So there's a little math here, so let's add up the numbers. If you combine the first and second harvest, then you obtain a harvest yield of 170%. If we then divide this by 75%, which was the yield from the depth filter, we see that using TFDF generates nearly 2.5 times more material. Granted, there are some additional steps are taken, such as adding more media, but the value of 2.5x should far outweigh that effort. From a technology level, that the low shear rate of TFDF preserves the integrity of the HEC-293 cells, even when operation at high flux, enabling altogether new lentivirus bioreactor applications. So earlier, I showed you a graph before of one harvest of pressures and flux versus time. So I want to show you the exact same graph here, but for the 2 harvests that we just described in the last slide. During harvest 1 at 700 LMH, TMP increases less than 1 PSI, again, essentially no fouling. Over the course of the second run, it rises a bit, but still only 2 PSI. Therefore, both harvests are completed with the same filter with a total of less than 3 PSI increase. So it's important for me to mention that the flow path that surrounds the filter is closed and gamma irradiated, which is a key enabler of these multiple harvests. We can essentially make the connection of the TFDF to the bioreactor and then process over extended time periods with negligible contamination or bioburden risk. So all the runs that we've looked at thus far were at the 5-liter scale. So are we able to show the same performance at larger scale? So we scaled the 5-liter tenfold up to a 50-liter scale reactor and found that the yield, the process time, and the filter fouling were very similar to the 5-liter scale. So yield, again, was greater than 90%, shown here in the bar graph. Flux was constant at over 750 LMH. And TMP ended below 1 PSI, and the operation was wrapped up in less than an hour. So the TFDF filter sizes are available at larger sizes, such that volumes of 200 liters and 500 liters, even up to 2,000 liters are feasible with the TFDF technology. So yes, it's scalable, which is also really will help you in your increase in your productivity. So the bigger we go in scale, the more challenging the operation becomes. Almost every process can be managed at small scale, not too difficult. It's at larger scales that where the rubber really meets the road and where TFDF really shines. Therefore, I just want to walk through what TFDF looks like if we were to scale another tenfold from 50 liters to 500 liters. We scale the TFDF process by adding more filtered tubes to the same enclosure. This means that the simplicity of TFDF carries from the 1 liter scale to the 50 liter scale to the 500 liter scale and beyond if needed. At each of these scales, you only have one device to unbox, install, and break down. Assembly and disassembly are completed in 20 minutes with only 3 connections using genderless aseptic connectors. All the pressure sensors, the magnetic pump head are already built into the flow path. In terms of space, the entire footprint of your skid and your filter is only about 10 square feet. This is because the filter mounts onto the skid with the pumps. It's really, really, really simple. And that simplicity scales. Also, there's no need to organize 20 parts during setup. There's no Wi-Fi flush. The filter ships dry, so it saves tons of very expensive water. There's no product flush at the end. There's no product mess spilling out during the breakdown. I've seen where you take apart, filters and you just have this mess of virus spilling out everywhere. There's no hardware dedicated to just holding the filters. That core concept of combined depth and tangential flow filtration create capacity and volumetric throughput that delivers more product much faster and in a much smaller footprint than classic depth filtration. Who couldn't use more product, extra time in their day, and extra room in the lab? It's obvious, right? So I'd love to dig deeper and go deeper into how the technology works and its other applications. But I'm going to have to wrap it up with this slide that simply describes the different components that work together to create the complete solution. It starts with the tubular depth filter in the blue there on the left. The first depth filter, let me emphasize, the first depth filter to act in tangential flow mode. We then take the TFDF filter, put it into a flow path that includes the filter, obviously. It has filter, it has tubing, clamps, pressure sensors, aseptic connectors, and the single-use pump head. So all of these put together, gamma rated, ready to use. The beauty is that at the small scale, you only have one device to unbox, install, and break down. And at large scale, you still only have one device to unbox, install, it's fast, just 3 connectors, putting it onto the skid, and to break down. Again, the ProConnex flow paths are all closed, gamma radiated, and they come as both stocked, off the shelf, and configurable models. You can configure the flow path, the tubing sizes, the aseptic connectors. The final component to the solution is the system, which includes automated process control logic specifically engineered for TFDF. TFDF systems, like the flow paths, scale from the lab to the pilot and then to large process scale. So just a quick acknowledgement to the several contributing authors to the Cell and Gene Therapy Insights publication. Just want to say thanks to Thomas Williams. These are from Oxford Biomedica. So Thomas Williams, Oliver Goodyear, Lee Davies, Carol Nevelman, Kyriakos Mitrofanous, James Miskin. They helped with in the publication of this paper. Finally, thank you for taking a few minutes to join us for this gene therapy showcase of Repligen technology. If you're interested in learning more about TFDF or exploring new applications, reach out to our, the salesperson or visit repligen.com/TFDF and you can get more information on our website. Thank you very much.